you find that although the loop is moving, but there's no change in flux because the B times A is a constant, correct? So once it's entirely inside, there is no changing flux, so there's no EMF, there's no current, there's no force at all. So the external agent that is moving it inside the loop, theoretically, it does no work. There's no need to exert any force. Then for the third part, when it's moving out, you find that a very similar scenario happens just as when it's moving in. Let's say that at some point in time, it has already moved out to a certain extent, and the distance now, right, the length of the coil that's still inside is x, and of course x is decreasing with time when it's moving out. So as moving out, x changing, so the flux is changing. In this case, the flux is decreasing with time, the flux through the loop. Agree? Okay, but we know that from Faraday's law, whether the flux is increasing, decreasing doesn't matter. So long as there's a rate of change, there's EMF induced. So there will be EMF induced, and if you analyze, the EMF induced is exactly the same as before. You'll be given by these expressions, right? Exactly the same expression, and the flux will be BWX also. B, which is the magnetic field, times W times X. And you get the same equation, you do the same thing, and dx dt is still the speed, therefore you get the same EMF induced. So when it's moving in or coming out, the EMF induced is identical. And the current is also the same because the current is just EMF divided by the resistance. Okay? So therefore we get everything the same for EMF or current. Now next, how about what's the direction of the current? Now we have to analyze. Well, again, we apply Lenz's law. We have a flux that is pointing into the loop, but this flux is getting weaker and weaker, isn't it? It's getting weaker. So Lenz's law says that the induced flux must oppose this changing flux. When something is getting weaker in this direction, the induced flux will be pointing in the same direction. Okay, so therefore the induced V must be pointing in, from which you deduce that the current must be going clockwise. Then as before, only this segment of the loop which is inside the magnetic field experiences a force. For the upper segment, the force is now directed up because it's IL cross B. You see that? And for the lower segment, it's IL cross B down. And this FB up and down, they are equal in magnitude. Therefore, the net force is 0 in the vertical direction. Then for this vertical segment, in fact, you already know. Without using the IL cross B, you know that the force must be opposing the motion for the same reason of conservation of energy. But if you want to analyze, it will be like this: IL cross B. Do you see that? L length vector cross B. Okay? So your thumb will be pointing to the left. Are you all clear about this? Okay, so hopefully by now you have forgotten all the rules of remembering which fingers for whatever quantity. That should be already dropped, right, from your memory, and just know that the equation is IL cross B. So L is the long direction of current, and wherever B is, I stretch my thumb, I get the resultant vector. Okay? So far, so good, everybody? Okay, if no question, then we move to question 3. Now, in